Assalamualaikum. Assalamualaikum. ये आपको स्क्रीन नजर आ रही है? कट तो नहीं मेरी वजह से। Start it now. So I have uploaded the course outline on LMS and also the course textbook, so you can have a look. And so what we're gonna do today is just continue from where we left last time. And as I was telling some student over here that I did charge up my tablet, which I'm most comfortable with, but it's still not connecting to the Windows. So I am still working on that problem. Should be solved in 1 or 2 classes. But I did some practice, so I think today's class will be much better than the last time in terms of writing. Now, let's start with the work right away. So last time we had a look at linear systems. So we looked at linear systems of algebraic equations. What does algebraic mean over here? Algebraic for now just means that we are not considering any derivatives or any integrals. No calculus concepts are involved. All you have is simple relations, some variables connected to some numbers and written in the form of an equation. And we look at them through examples. Didn't define them very carefully, just right away started to look at examples. And so I'm gonna repeat the first example we did today, and we solved it by using the usual method which you studied in high school algebra, well, even in the middle school algebra. So what was the method? You had to eliminate variables one by one. Variables one by one. And when you're left with only one last variable, then that has the solution for that variable, and then you back substitute to get the rest of them. And how can you do it? By doing some allowed operations. Allowed operations on your equations. What are those allowed operations? Well, say again. So allowed operations, you all know what you can do. You can multiply one single equation, any single equation. So in the system, you have many equations. You are allowed to multiply any single one of them or any number of them by a number, right? Everyone knows that. By a number. Then we are also allowed to add one equation to another. Multiply by a number, by a number, and add to another equation. another equation in your system. So take one equation, multiply it with any number you like, and you add it to another equation. So these are the allowed operations. Doesn't change the system. What you get, you start generating new equations. Those are equivalent to your original system. Nothing has changed. The new equations are also statements about the same variables. So we took this example. We had x minus 3y plus z is equal to minus 6, and then we had 2x plus 2y minus z equals to 10, and the last equation was 3x minus 2y plus z, and this is equal to 5. Now again, just a warning that this is very, very simple. So almost all of you must be knowing what to do with these equations. So this is just repetition of what you already know. So but what we are doing is trying to eliminate these variables one by one. So I take this x, so I can first try to eliminate these guys, x's, and what I would my goal would be to get two equations involving y and z. So once I have two equations involving y and z, then I can eliminate y and get one equation involving z. So at each step, I'll reduce one equation. So how can you do that? Well, very simple. It's obvious from here that if I multiply first equation by minus 2 and add to the second equation, the x will be gone. I'll get an equation which will not have an x. Similarly, if I multiply first equation by minus 3 and add to third equation, I'll get an equation which will not have, again, not have an x. And when you do that, you get these equations. 8x minus 3z is equal to 22. Because I had a minus 6 here, multiplied with minus 2, you get a 12, and you add it to 10, you get 22. Then I have 7x minus 2z equals to 23. So you got two equations. Now, in these equations, this is not x, this is y. So this is, you got two equations involving y and z. Now, you can multiply the first equation by minus 7 over 8 and add it to the second, and you will get, this way you will be eliminating y. And you get an equation you get 5 over 8 z equals to 15 over 4. So this gives you z is equal to 6. So in this way, you always get value of the one last variable which is left. Now, what you're gonna do now, you're gonna just complete the solution. Now these new equations which you have generated, like the one over here, this one, or this one, or this one, these are all the statements about the same system. So you can collect some of these and call it a new system. It would not be a new system. It will be equivalent to your original system. So you have just given a new shape, a new form, new description to the same system. Now, for back substitution, it's to make it more systematic. It's best that, so what you're gonna do now is pick one equation. So you have got one equation involving z only. Then you're gonna pick one equation involving y and z, and one equation which involves x as well. So this way you will be able to back substitute. So it's your choice which one you want to pick. So I'm just gonna pick the first one of these pairs which have these properties. So I pick this, the first equation involving y, x, y, and z. And one of this equation, 7y minus 2z. You can pick any one, doesn't matter. 23. And the last equation I'm just going to write like this. Now you have the solution for z. You put it back over here, compute this number, and that will solve for y. So you got your y. And if you do that, you find your x is, your y is 5. Z is 6, y is 5. Now you take these values and plug them over here. So you will have instead of y and z in this equation, you will now have numbers. So you have a solution for x right in front of you. So you can do that and you will get x is equal to 3. So this way you have a step-by-step algorithm how to solve these equations. Eliminate the variables one by one by multiplying some equation and adding to the other, and then collect these equations which involve more and more variables, and then you can do back substitution. So this system, by picking one equation involving z only, one equation involving y and z, and one equation involving x, y, and z. So this equation is called, this system of equations is called strictly triangular. So what is a strictly triangular system? So if you have 3 variables, what you're going to have is you are numbering those variables in some way. So like x is your first variable here, y is second, and z is your third. So in the first equation, the coefficient of x is not 0. In the second equation, the coefficient of x must be 0, but that of y must not be 0. And in the third one, both x and y, their coefficients are 0. They are not present in that equation, but the coefficient of the third variable must not be 0. And you keep going like that. So in each next equation, you are eliminating more and more variables. But the next variable which is present, it must not be eliminated. If you have such a situation, so like over here, then you call it strictly triangular. So for example, if this equation, there was no y over here, it would still be triangular, but not strictly triangular. So because it looks like a triangle. And you can use this triangular system to back substitute. Now, the important point is that this system of equations is no different from the previous, because we got it from the original system by allowed operations. So these are equivalent systems. And we discussed it last time that the equivalent systems have same solutions. And vice versa. If you have 2 systems, how would you know that they are equivalent? One process could be that you try to convert one into the other by using allowed operations. but it may take you a lot of time. If you could solve the two systems by any method, and you know their solutions, if the solution set is same, all the solutions of one system are also the solutions of the other system, then those two systems are equivalent. But this one I know is equivalent because I got it from the first one to some allowed operations. So your goal is to get to a strictly triangular system by using allowed operations, and once you have it, you get your solutions by back substitution. So that's the algorithm for us for now. So any questions so far? Yes. Yeah, let me write. And so the question was, can you write an example of something which is triangular but not strictly triangular? So let's suppose I have 4 variables, x1, x2, x3, and x4, and I have a system like this. By the way, this strictly triangular system, I'll talk only about n by n systems. So this term is reserved for n by n system. And right now, the algorithm which I am giving you, I forgot to say it in the beginning, because so much is going on in this class, is that we are for now solving n by n systems. N by n system, you know what it means. It means n variables and you are given n equations. So you have n equations to play with and you are looking for n unknowns. So for an n by n system, you have this term strictly triangular system. And I'm giving you an example of an n by n system. So you have a 4 by 4 system. You have 4 variables. And I'm just writing some relation. x2, x3 minus 6, x4 is equal to 7. Well, let me change it a little bit. And then I have x3, and then I have 5, x4 is equal to minus 3. So this is not strictly triangular because you expected, you are coming down. So you have a numbering for it. It depends on the numbering of as well. So your first variable over here is x1 and your first equation starts with x1. You want your second equation to not have any x1, but you want it to start with x2. If it's not starting with x2, it's starting with x3, it's still triangular, but not strictly triangular because you expected something over here. Instead, you got a 0 over here. So now this example which we did over here, I'm going to do this same example, but in a somewhat clutter-free way. So what's the clutter-free way? So you should think of it for now as just cleaning up my screen, your paper. Now, if you look at the way I'm writing these equations, I write x's below x's, y's below y's, and z's below z's. So if I always stick to some convention that I'm going to write x first, then the y, then the z, then I don't even need to write them because I know I can just collect these coefficients and put them in some order. And I would know that the first number which is coming in must be the coefficient of x. The second number must be the coefficient of y. Once I stick to some convention in my mind. And the next is z and so on. So I don't need to write x, y, and z just to make it a little bit more clean. So just one second. So I have in mind, like for that equation, this convention that first I write x, then I write y, then I write z. Then those three equations I can write like this. This is the first equation. All I need is the coefficients. The coefficient of x is 1, coefficient of y was -3, coefficient of z is 1, and this was equal to -6. So the last thing which is coming in is the number on the other side of the equality. And what was the second equation? So it was 2 minus 1, and on the other side you had a 10. Similarly, the last equation was 3x minus 2y and plus 1, and this is equal to 5. So this convention, once you have chosen it, just these numbers, and this looks more tidy, at least more neat to look at, more easier to read, gives you all the information you had about those systems of equations. But remember that you have a convention and you are putting these numbers in very specific orders. So this thing, when you put these numbers, a collection of numbers in a very specific array of numbers, whenever you use them, well, if you had just one line, sometimes you call them a list. But if you have like a two-dimensional array, you have a name for it. You are used to calling it matrix. So we can also call this thing a matrix. Let me just put some dotted lines here, because on the other side of this line are the equality numbers, and on the left hand side of this dotted line are the coefficients in front of the variables in my equations. So this matrix which you have constructed is associated, it's a matrix associated with your linear systems. This is called Augmented Matrix. Let me for now write the full name. Associated, later on I'll not say the mouthful thing, associated with system of equations. So if you are given this, you know everything, you know the equations which are given to you. You can construct them. And sometimes it's useful, well, many times it's useful to just write this part, which gives you the coefficients of the variables. So if you just stick to them, these guys, so this is part of the augmented matrix. This is called the matrix of coefficient matrix. Or CM, and this guy is called AM. The nice thing about CM, why sometimes we talk about it, is that if you're considering an n by n system, then it would be a square matrix. It would be an n by n matrix. So over here, it's a 3 by 3 matrix, while the augmented matrix has one extra column. So it's if you have a 3 by 3 system, you will get a 3 by 4 matrix. If you have a n by n system, you will have a n by n plus 1 matrix. And let me just state these two facts over here. Note them down again, that the row of augmented matrix are giving you, each row is giving you one equation. In this system. And what does each column give? Yeah. Coefficients of one type of variables. Of one specific variable. So like, if I pick this row, 2, 2 minus 1, 10, this is giving me this equation, 2x plus 2y minus z is equal to 10. And if I see like y, what are its coefficients? I know that in my augmented matrix or my coefficient matrix, the second column would be 3, minus 3, 2, minus 2. Over here, minus 3, 2, minus 2. Now, if you are given a system, as we saw, that you can do some allowed operations and change it into some other system of equations, which looks something else, although it's equivalent to the first one. So you can do the same things so that means if I start with a system, I can change this system by doing some allowed operations and to get another system, and there will be a matrix associated with that system, with the new system. So I had gotten a new matrix, which was this one. My triangular system, which I had gotten, looked like this. So 6. And over here, I had zeros. So this augmented matrix, because this represents the transformed form of those equations, should be somehow also associated to my system. And this is that form from where I can read off the solution by doing back substitution. That means that if you construct one matrix associated with a system, then you should be allowed to make some operations on that matrix to get to some other related matrix which is associated with the new system which you got by doing allowed operations on the equations. So the allowed operations on the equations translate to allowed operations on the matrix associated with those equations. So what would be those allowed operations? So I'm going to repeat the solution. But now using these matrices. So it's just the same method done in a clutter-free way. So goal would be to bring my original matrix which I constructed to this form. Goal is to transform the augmented matrix to strictly triangular form. What is the strictly triangular form over here? The associated matrix, matrix of coefficients, the CM, should be in the strictly triangular form. There's nothing below the diagonal, and the diagonal is non-zero. Triangular form. Because if you do that, then you will have the solution by back substitution. And how are you going to do it? Using some allowed operations. So what are the allowed operations? So these are, you're just deriving them from equations. You have the allowed operations for the equation. You are just translating it to this new notation which you have adopted, this clutter-free notation. So one thing to note would be that each row is just one equation. And how I number the equations, that doesn't matter. If I write one equation above the other, that should not change the system. It's still the same system. So that means the numbering of equations doesn't matter. That means the rows in the matrix, you can interchange them. You can write the first row instead of the second, exchange first with the second or with the third or with any of the rows. So interchange any rows. You still have the same system. You literally did nothing. So the new matrix you get is still the matrix of your system. And then just like in an equation, you can multiply with a number. So what would happen to the matrix if you multiply the equation with a number? That corresponding row, the row corresponding to that equation will get multiplied with that number, right? So multiply a row. I hope we don't lose the internet. With a number. And what would be the third one? So it would be, you can multiply one equation and add it to the other. So that corresponds to multiplying. So when you multiply one equation, what happens? Only the coefficients of all the variables, they get multiplied with that number. And also the number on the other side of equality gets multiplied with that number. So that means the whole row in the matrix gets multiplied with that number. And then you add it to the other. When you add an equation to the other equation, what you do? Let's go back over here. You just add the coefficients because x gets added to x. So you just add the coefficients of the corresponding variables. So that means you are column by column adding the rows to the other rows of the matrix. Multiply a row with a number and add to another row. So these are the things which we were doing with the equations translated into the matrix form. So any question? No. So the question is, what does interchange of row means? If I interchange this row with this row, what that means essentially is I wrote this equation first and the other equation down. How is it going to change anything? कोई मैट्रिक्स की प्रॉपर्टीज नहीं है. Matrix, there's no matrix over here. Matrix is just a name. We are thinking in terms of equations. Any other question? It would be very helpful if you think that you never heard of matrices. We're going to develop all the properties of matrices. For the first time, that why we even do those operations with the matrices. So right now, think of the matrix as just some arrays, just a clutter-free notations for these equations. And these operations which I have told you, these are just operations on the equations. Just think about them. What's the multiplying a row and adding to another row? You are taking, so when I multiply this row by -2 and add it to this row, what happens to the coefficients in the new equations to coefficients of this? This gets multiplied, only the coefficient of y gets multiplied with -2, and then you add this coefficient to the coefficient of y. This doesn't get mixed with the x. That means in the matrix, when you clutter free this notation, the corresponding row will be replaced by this operation, that you multiply this number by -2 and add it to this number below it. So I'm going to just do this example and then it would be clear. So exactly the same, there was a question. So exactly the same example now done in this clutter-free way. So let me write this matrix again. -6, 2, 2, -1, 10, 3, -2, +1, 5. So that's the system of equations. And you wanted to eliminate the x. So in this thing, it would correspond to making this column, bringing it in this form that you have a two zeros over here. So start with this number. So we call this, we start with this. We're going to leave this row unchanged. So this is called the pivotal row. And this is pivot. There's some jargon, no inherent value to it. It's just what you're going to do. Take this number and make everything below it 0. And how can you do it? You're adding rows. So obviously, if I multiply this row by -2 and add it to this, this will become 0. And multiply this way by -3 and add it to this, this will become 0. So multiply by -2 and add it to this row. The goal is to make these zeros. And multiply this pivotal row by, because these are your allowed operations, -3 and add it to this row. So what do you get? You get, nothing happens to this. Over here, I know by construction, I'm going to get zeros. Multiplied by -2, you get a 6. 6 plus 2, 8. You get -3 here. Over here, you get 22. You can check. So -2 plus -1, you get a -3. And over here, you get 7, -2, and 23. So now you are shaping it, bringing it to the triangular form. So what next you need anything below this to be 0 to make it triangular. So now you say that I'm going to leave this as it is. The first row is already in the correct form. Now this is my pivotal row. And this is my pivot, this guy. I'm going to multiply this row by something and add to the next row so that this becomes 0. So then the answer is extremely obvious. You multiply by minus 7/8 and add to this. So you will get, and now you can see that adding is now very, very obvious. Well, at least to your eyes, it's much easier to add. And for now, this is the only advantage we are getting out of it. But later on, this notation, clutter-free notation, will prove to be extremely useful. (22). Here you obviously get 0, and here you get 5/8, and here 15/4. So this is the same triangular system which you had gotten using equations. Now you got it using this clutter-free notation. I'm again saying using this word because the moment you say matrix, you start thinking about what you learned in your high school. So this is just a notation, but we have a name for it. We call it a matrix. Any question? Now let us do. The problem is that we are going at an extremely slow pace. I'm really unhappy about it because we have to cover a lot. I hope that the pace increases once I get my tablet. So let us do another example. And you are given this system. And just to make it easier to make the matrix, I'm writing them with an indent. I have 4 variables and 4 relations because for now I'm only solving n by n systems, which you also call the square systems. So that is the first equation. This is the second. And this is the third relation. Sorry, this is a -1. And the last equation is plus 2x4 is equal to 3. So you have 4 variables and 4 equations. Now if I ask you that what is the matrix of it, the augmented matrix, it's extremely simple to write. Just collect these numbers. So what's the first element? 0, because there's nothing in front of x1. So you're just collecting these guys. And then you have 1, 1, 1, 1, 6, 2, 4, 1, -2, -1, and 3, 1, -2, +2, and 3. So that's your matrix, and you want to bring it to the triangular form by strictly triangular form by doing the Laud operations. Yes, what's the question? Yeah, because well, what do you mean by always? If your goal is to solve the system of equations, then the algorithm is bring it to triangular form, because then you can back substitute. Now, the problem with this matrix is twofold. First of all, to get strictly triangular form, I should have a 1 over here. Oh, not 1, any number over here, no, but not 0. But there's a 0. And also, if I use this, so I told you the algorithm, leave the first row and start bringing zeros over here. No matter what I multiply this 0 with, if I add it to the next rows, they're not going to change, because anything multiplied with 0 is still 0. So I can't change these rows using this thing. So I have kind of a failure. But I can get out of it very easily, because I have this allowed operation that I can interchange rows. That's completely okay. So I can take this matrix and interchange these rows. This row, the first 2 rows, I'm just going to change those. I could change it with the third row as well, the first with the third, that would be fine, but I'm just doing it with the second. And the advantage is also that the second row has a 1 over there. So it's easier to think that what should I multiply 1 with to get zeros below it. So here comes the first row, the new first row, which was the second row before. And here is the old first row, but the new second row. Now, what you're gonna do is make.
Sir,
yeah.
In the second row, it should be 0.
Should I repeat it?
In the second row,
okay, so
you wrote 6 instead of 0.
Say again.
In the second row, you wrote 6 instead of 0.
Sorry. Yeah. I'm hearing you through speaker, so that's why I'm having problem.
There also should it be -1? The third column in the second row.
It's a -1, thank you. Yeah, now I think we are fine. Now I want to bring zeros below it. So in the second row, I don't even have to do anything. There's already a 0 over there. So I do this, multiply the first row by -2 and add it to the third row. And multiply the first row by -3 and add it to the fourth row. Yeah. Because it's already 0, I don't need to do anything. So my goal is, what I'm doing, I'm first picking this pivot. What does it mean? That pivot means that I'm going to make everything below it 0. Because the goal is to progressively bring it to the triangular form. So make everything below it 0. The second row entry below it was already 0. I didn't have to do anything. Say again? I have not done anything. I'm going to write the answer in the next. What are you talking about? I don't get it. So this lasso tool, so when I do those operations, the first and second rows, they remain same. Why can't I select it? So my one node is kind of stuck. I don't know why. Should I undo it? None of that helps because it's stuck at this writing. Okay. So now the first and second row remain the same. Over here, I get zeros. I know I just did it by design. And over here, these rows are going to change. And you should be doing it on your own right now. Let me just write the answer. It's 2. Let's look over here. So -2 plus 4. So that's a 2. -2 plus 1. That's a -1. And -2 into -2 plus -2, that's a -4. -12 into -1, that's a -13. And similarly over here, I get -2, -5, -1, and -15. Now, I'm going to take this as pivot. So this guy is the pivot now. This guy. And I'm going to multiply it with something and add it to this. I'm going to make a 0 over here. So all I have to do is multiply it by 2 and add to it. And then multiply it by -2 and add to it. So when you do that, you get again these rows remain same. You should be doing it with me. These I know are going to be 0 by construction. And over here, I get a -3 and a -2 and a -13 because above it was a 0. It doesn't change anything over here. And over here, I get a -3, a -3, and -15. So kindly keep checking it that I'm not making a mistake. Now what you need to do, now again, now this guy is your pivot. Move on to the next row. This guy is your pivot, and you have to bring a 0 over here. So all you need to do is multiply this row by -1 and add, and you get this guy, only this row is going to change. And what do you get over here? You get a 0, a -1, and a -2. So you have brought this to a strictly triangular form. That means now you have a solution. So what's the solution? Well, the last equation, you can read it off over here. The last equation associated with this matrix is just -x4 is equal to -2. So that means x4 is -2. 2. And the equation above it, what does that say? That says -3x3. With some practice, you don't even have to write these equations. -2x4 is equal to -13. So you put this value of 2 over here. And this gives you the value for x3, 3. Now I'm not even going to write the equation. I go above over here. For x4, I put a 2. So 2 times 1, 2. And I put a 3 over here. 3 times -3 is a -3. And you are adding over here. It's an equation. -3 plus 2 is a -1. And this is a coefficient of -x2. So that equation is saying -x2 minus 1 is equal to 0. So that means x2 is equal to 1. x2 is equal to -1 because you got a -3 plus 2, which is -1. So x2 is equal to -1. And similarly, you can find by putting these values over here that x1 is equal to 2. So this way you have solved the system, but in this clutter-free way. The only advantage for now is that you can very easily see, look at this row, look at any pivot and see what numbers I have to eliminate below it. And just multiply that row and add down there. So any question? Yeah. Now this procedure should have convinced you of this little theorem. So what does this theorem say? If it's not a very useful theorem in the sense that it doesn't give you an algorithm, but it tells you a condition. If an n by n system can be reduced to a strictly triangular form, reduced in what way? Using the allowed operations. If an n by n system, it's only about n by n system, square systems, same number of variables as equation, can be brought to a strictly triangular form, using allowed operations. Those allowed operations, when you do it in the form of matrix, they are also given another name. They are called elementary This went off. Can you guys hear me over the Zoom? Can someone answer?
Yes.
Okay. No problem.
Yes, sir.
Okay, thank you. So these are also called, when you do it in the matrix notation, they're called elementary row operations. The three I listed over there. So if an n by n system can be brought to a strictly triangular form, we will have a unique solution. Oh, what happened? They're not really technologically equipped to run these classes, and I don't know why these guys don't stay here. Hello? Walaikum salam. Walaikum salam. आप कौन बात कर रहे हैं? Can you go out and see if there's someone? Even Zoom is not connected, or is it connected? So let me tell people who are connected to Zoom. So we were projecting it, and there is a problem. Our projector just went blank. So now, are you guys connected again?
Yes, sir.
Yes, sir.
So did someone went out? या इससे बहुत बेटर है कि आप फिजिकल कनेक्शन दे दें. ये तो बहुत प्रॉब्लम ऐसे होता ही है ना. वो बंद हो गया देखें ना प्रोजेक्शन, क्योंकि इंटरनेट वेंट आउट. इंटरनेट इज नॉट स्टेबल एट ऑल. अभी मेरा जूम डिस्कनेक्ट हुआ है और उससे पहले ये बंद।
लाइन लगा दो
लगा दो। अभी तो कर दें, अभी इतना टाइम नहीं, 10 मिनट की तो क्लास रहेगी। कीवर्ड क्या? इसमें देखें लैन है, इसमें नेक्स्ट टाइम लैन लगा लेंगे। कीवर्ड क्या? याद नहीं?
वो रिफ्रेश करने चेंज हो जाता है।
इतने इसमें सिक्योरिटी डालने की जरूरत क्या है?
वो सर इसलिए अगर कीवर्ड नहीं डालेंगे तो क्या नाम है, कोई स्टूडेंट भी अगर लर्न पे कर रहे हैं उसके पास भी डायरेक्टली करेगा।
So now can you tell me over the Zoom, can you hear me?
Yes, sir.
Okay, thank you. So the theorem, so just these examples, they demonstrate this theorem, and it should have kind of, its proof is obvious, that if you can bring by these allowed operations system to strictly triangular form, then all you have to do is do the back substitution. And since the two systems are equivalent, you brought one to the other using allowed operations, so they have I mean, they want to run online classes, but they don't even have a stable internet. Restrict क्यों किया हुआ? Don't they want to run classes? Now, how do I share screen? Now this is gone. Okay. Let me just say in words. So you have got everything which you need to hear these words out and kind of construct the proof of this theorem. It's only the half of the material which I had planned for today, and we can't be going at this pace for too long. There has to be a solution for these problems. In any case, so theorem says that if you can bring a system, so you can bring the n by n coefficient matrix to strictly triangular form using these elementary row operations, then you will have a unique solution. Not only you will have a solution, but it will be unique, because the last element, when you have a strictly triangular form, the last equation is telling you only one number for the last variable. Like in this case, it was x4 is equal to 2. Now the equations above them are also, so the equation above it have the x3 in it, and once you put this unique value of x4, you will have a unique answer for x3, and so on. So you keep back substituting, and every time you get a unique answer for a variable. So finally you end up with a unique solution. So it's a little theorem, but it's very revealing. It says if you can bring any n by n system using these allowed row operations to a strictly triangular form, then you will have a unique solution. So we will have to end the class here, and we have kind of missed out. We have missed out one class because it was cancelled, and in essence we have only done one class worth of work in these two classes. So I hope we are given the opportunity to make up for this time. And any question from people over there across Zoom? I had to stop here because there are many students who are present and they didn't bring their laptops, so they have to see the projected screen, and the projected screen is not working. So that's why I had to stop here. I'm just letting know people who are watching through Zoom. And let's try. I showed up here like half an hour before, but still we ended up with lots of these technical problems. I'll from my end try to solve these problems. I go out in the market, I try to solve them on my own. There is not much happening. Still we are encountering problems. I'll do whatever I can to solve these. Okay, see you on Thursday. Yes, okay. Next time 9 seconds. So how do I stop this?